mostly. So on the stream, sorry about that. If you got cut off, here's part 2. Let me just copy this back down here. That was exciting. Okay. Back down. I'll put it up on the screen, don't worry. There we go. I think it's been about a month since I've rebooted anyway, so it's probably good for the computer, don't you think? Okay, so here we go. Let's see how we did. Now that I've got myself straightened out. Okay, and let me double check. It is recording. Sound is on. It seems a little hot. The mic is reduced there. That might be better. All right, let me find a volunteer. Hold on a sec. Yeah, by the way, I guess that this would be a good reason to go grab your stuff at some point. You don't have to do it now, but that way you'll have, like on the quizzes, you have the chart. Oh, I should just give you this quiz now. We aren't going to take it for real today, so don't worry. This way you have a chart of sorts. I think there's 4 there. You need 5. There's 7. So yeah, Adam can get one from Bruce folks in here. There wasn't an extra one? There's one for Adam. All right. Yeah, we'll do this quiz together in just a bit, but this way you have the table there on the left. You got one? Everyone's got one. Good. So you've got that table, you can refer to it. At any rate, let's go ahead and see how we do with this. And that person isn't even here, so I'm going to try another one. Jackson's here. Jackson, what do you think of this first one? Were you able to come up with the Laplace transform of this thing?
E to the pi of 6s times
Very good. Yes, 1 over s squared plus 1. It's kind of confusing. So what you could do is you could take this and say we're going to do the Laplace transform of sine of t. And that's what ends up there. Yeah, so very good, very good. So probably if you had this as a problem in your book, they would write it like this, e to the negative pi over 6s all over s squared plus 1. Just combine it as a single expression. What do you think, Peyton?
Would there ever be a circumstance where it's e to the positive something s?
I can't think of a situation where I've seen that. The problem is that we mark time moving forward, and so that would be like, well, 2 days ago we turned this switch on. Well, we don't care because we're starting the timer right now. So yeah, one of the things, the way I always think of this is that this is when you turn on the function. And so if we're starting to observe whatever's happening, if something's already on before we start observing it, then we don't care when it got turned on. Like right now, the lights are on back there. I don't know when they got turned on today, but if I start my stopwatch now, they're on, so I don't have to worry about any Heaviside function for those lights, or that function. All right, next. So any other questions about this one? That was pretty straightforward. It's just taking out that sign of t is a big problem, but not a big problem, it's easy. All right, next, let's do the second one. I think we can do it. Bryant, what did you get for this second one?
e to the negative 5s times 2 over s cubed.
Nice, excellent. And once again, it's this thing that we're going to take the Laplace transform of t squared and stick it right there. Very nice. Now we have a problem, don't we? Yeah, so typically, if you were actually wanting to observe or maybe set up a differential equation that involved a Heaviside function, you wouldn't necessarily be able to time the starting, the beginning of whatever it is that's going, turning it on or whatever it is, with whatever function is over here. So we're going to have one more tool, one more formula, but it's not a big deal. And I should say that that formula you'll see is not on this little quiz table, but it is related to one of the ones in that quiz table. So let me show you where I'm going to get this formula. So here is what, whoops, a minute, trying to copy that. I'm going to paste it down here because I don't want to have to rewrite. There, so it's related to this, and what I would like is something like this. The Laplace transform of the Heaviside function shifted by a units times some function that is not shifted. So you might say, how in the world are you going to do this? Well, the way that I'm going to do this is this. I'm going to do the Laplace transform of the Heaviside function times f of t plus a minus a. And so it's basically the same as what's up there in the red. You have e to the negative as times the Laplace transform of f of t plus a. So this line here is just an intermediate step to show you where this is coming from. But essentially, if you're going to multiply by a Heaviside function, you've got to do some shifting somewhere. And so if the shifting isn't already embedded in your function like it was with that sine curve, you're going to have to take it off somewhere, and it's going to go right there. So let's go back up here, and I'll get you started on this one. Let's see, can I zoom out a little bit? Yes, I can. You can see it all. It's at the bottom there. And so here's how this looks, is I'm going to do this. The Laplace, or here. Maybe I'll just do this. Here. Yeah, I guess I'll just do this one. I know, you probably could figure it out. But negative 3s times the Laplace transform of t plus 3 cubed plus 2 times t plus 3. Now, this is still going to be a bit of a pain. However, it's not as bad as trying to sort through how far you're supposed to shift all that stuff. I've done that in the past, and this is just way easier. So here's how this, you can see what I've done, hopefully. I've just changed all the t's to t plus 3. And now I can do a little bit of algebra. And I know it's a little bit of a pain, but we can do it. So this is going to be e to the negative 3s times the Laplace transform of, we've got t cubed plus 9t squared plus, give me a sec here, 27t plus 27 plus 2t plus 3. Yeah, I think I got it all. So you might wonder, where did this stuff come from? It's because I happen to know how to cube a binomial. That's where this came from, is cubing this binomial right here. And then the rest of it, of course, oh, almost. The rest of it, of course, you could see exactly where it came from. The 2t plus 6 is just 2 times quantity, t plus 3. And then at this point, you can all do the Laplace transform of this. I know there's like 5 things there, but you can combine a few of them and then follow the table here, and you'll get all of the component parts. in fact, I'll just do this, negative 3s times, I'll put this in brackets just to say this, all of this is multiplied by e to the negative 3s. So we've got 6 over s to the 4th plus, let's see, that's going to be 18 over s to the 3rd. And then 27t plus this 2t makes 29t. So that's going to be 29 over s squared. And then 27 plus this 6 makes 33. So that's just going to be 33 over s. So let's box this thing up. And that's it, for what it's worth. So anyway, on your homework, which I know I'm getting ahead of myself, homework preview, but your homework for this weekend is all Heaviside functions. Sadly, you don't have the hammer until Wednesday's homework, which coincides with the exam. There is a practice exam already online, but yeah, I could delay Wednesday's homework to be the following Wednesday, but we'll see how far we get. So anyway, little quick homework preview is that you're going to be doing two things on your homework. One thing you're going to do is what we just did. Find the Laplace transform of some Heaviside function times another function. Another thing you're going to do is you're going to do, oh, wait a minute, this is the wrong quiz. Do you guys have, how is this the wrong quiz? Why did I print that?
Oh, we have the top one.
Oh, the top one is the one, oh, I know what I did. I took this quiz and then I edited it, and I only edited the top half, not the bottom. Okay, so yeah, this is the quiz that I hope. So I'm glad I'm not doing it for real, a real quiz, because yeah, that bottom quiz, that's the hammer. We'll get to that. For now, though, let's take a look at this. Sorry if you have the one that I have here is the wrong one. So just copy this down. And we're going to go through this, and we'll work through this together. Not to fear. It'll be okay. What's it?
It's the Dirac, whatever.
Yeah, the Dirac delta function.
Yeah, we found the table for it.
Oh, yeah. Oh, it's on my table.
It's not fun.
Yeah, it's not bad, but it'd be nice to know what it means. And what it means is over there. We'll get there. So something exciting, right? Okay, so let's do this. And so the first step, of course, is to do the Laplace transform of each term. So let's go ahead and just do this one term at a time. And I will do this maybe with different colors so that you can distinguish. So we'll start with y prime. So Sam, can you do the Laplace transform of y prime for us? Wait, you don't have the chart?
Or is this the correct one on here? This is the one too.
It doesn't matter. It's the same. Yes, the chart's the same. So it's at the bottom.
Oh yeah, that's good. So that would be S times the Laplace transform of y to the 2 of step 1. And minus the initial function.
Okay, the initial condition happens to be 0. All right, very nice. Okay. Next, we have to do 4 times y. So let's do that. So plus this thing. So how would I write the Laplace transform of 4 times y? What do you think, Darren? What am I going to do with that?
Let's just 4 times the Laplace transform of 5t.
Of y, you say?
Yeah.
Okay. Oh, y of t. That's
Yeah.
what you said. I'm sorry. I said 5t.
No, it's
Where's
what I
the
heard.
5 coming from? Okay, no. Yeah, y of t. Yeah, technically I should be writing it as a function of t, but I'm too lazy to do that, so I'm just going to write it like this. Okay, next. We've got, Megan, what do you think of u of t minus 2?
2 F over F.
Over S, very good, excellent. We're doing great. Avin, what about minus u of t minus 4?
That would be minus e to the negative 4s over f.
All right, same thing as what Megan said. Oh, I didn't color code those. I can always highlight them, I guess. So there's this one, and then the other one is the unhighlighted one. Okay, but that's, yeah, it's pretty straightforward, isn't it? Okay, so your next challenge, if we're going to solve this differential equation using Laplace transforms, is you're going to solve this for L of y. So take a minute, solve that for L of y. So hopefully you're doing something like this. It's a little bit of algebra, not too challenging. So you factor out the L of y, and you get s plus 4. And then we're going to divide both sides by this, excuse me, so that I've got L of y is e to the negative 2s, whoa, sorry, ss, 2s, you know what, I'm going to combine these. All right, so that wasn't too bad either. Now for the thing that's not, well, it's not a bad one. Here, let's see. It's all of the, this one's actually a pretty good problem in terms of Laplace transforms. So here's what I might suggest you do, and then we'll get you to do the final step. So we've got e to the negative 2s minus e to the negative 4s times 1 over s times s plus 4. Okay, some of you probably can sense what is coming, and what is coming is that we have to deal with this right here using partial fractions. But it's not bad. This one's, you could almost, I'll bet some of you could work this one out in your heads. But here's the partial fractions. See if you can do this yourselves, either just by doing, like, being able to eyeball it, if you will, or actually do the work. I'll do the work in just a minute, but I just want to give you another little practice. Whoops, I have a close parenthesis there. All right, so I've got mine, I got a equals 1/4, b equals negative 1/4. Oh, nice. Yeah, like I said, you probably could have, some of you might be able to just say, you know, eyeball that and say, oh yeah, it's going to be 1/4, negative 1/4, just based on experience with this stuff. But it's fine if you couldn't do that. So that means that what I'm dealing with is I'm dealing with this. So Okay. I'm gonna compromise with myself. I was gonna skip a step, but I will not skip that step. I'll put that step in right here. So using that stuff, I've got this 1/4 over S plus negative 1/4 over S plus 4. Okay, now for this, I was going to skip that step, but let's just, we can do this. So I've got 1/4 e to the negative 2s over s minus 1/4 e to the negative 4s over s plus, oh, I guess that's minus 1/4 e to the negative 2s over s plus 4. I'm doing FOIL, by the way. I should have mentioned that. Plus 1/4 times, let's get rid of that, e to the negative 4s over s plus 4. Okay, so that's FOIL with the there. So double check, make sure it makes sense, and then we're going to do the inverse Laplace transform of each term for this thing. I'll give you a minute to check all of my algebra. And then we'll do one term at a time, don't worry. Plenty of time. All right, hopefully you're getting started on this inverse Laplace transform. All right, let's just go around and figure out what we got. Aaron, what do you got for this first thing here, the 1/4 e to the negative 2s over s?
I got 1/4 times t minus 2.
So that's u of t minus t, right?
Yep.
Yeah, very good. All right, very good. Okay, my next one is, oh, not here. I'm sure you could have done it. Reagan, what about this next one, the 1/4 e to the negative 4s over s?
Negative 1/4, that's t
T minus 4, very nice. Okay, next, we've got, not here, but I'm sure you could have done it. Peyton is here, though. What do you think of that next one, the 1/4 e to the negative 2s over s plus 4? So just build it like little building blocks, like Legos. We got the 1/4, I'll put that down.
Yeah, so, 1/4 u t minus 2 times e to the negative 14.
Negative 14. Okay, so t minus 2. So yeah, so I know this it's hard to get into this. So here's how this shakes out: is you've got this piece, which turns into that, and then this thing. I could find a different color. That thing should be exactly what Peyton said, which is e to the negative 4t. But bear in mind, we're doing inverse Laplace transform of this, so we have to shift the whole thing, t minus 2. So then it ends up being like that. All right, let's try the last one. I know this is hard, so take your time. We'll do this last one plus. Rostin, what do you think that last piece there? Can you do that one?
Plus 1/4 u t minus 4 times e to the negative 4 times t minus 4.
Yeah, perfect. Good. All right. One of the things I find amazing, I don't want to take the time right now to do this, but I can graph this function. So this thing here, I can graph this. You can graph this on your calculator, actually. Okay, I'll have to show you maybe on Monday how to do that. What you do is you use the test. So if you wanted to type this into your calculator, one of these TI calculators, there's a test button. And so what you would do is you would do, let me just show you with this one right here, you would do 1/4 times x is, let's see, it's t minus 2, so x is greater than or equal to 2 times e to the negative 4 times x minus 2. That's the way I would type that in. And the way you get that greater than or equal to is you press second math, so it's above math, and you'll find greater than or equal to, and you can, stick that in there. And basically that does the same as a Heaviside function. So if you do x is greater than or equal to 2, then it'll do that. But anyway, the reason I mention this is that if you graph this function, which has all of these things that seem like it's a piecewise function, seems like it would be completely discontinuous, doesn't it? With all this stuff going on, turns out that this function is continuous. It is totally continuous, even though it's got all this mess going on. So despite the fact that you have this thing jutting up, this down, things will cancel, interestingly, and it works out that it's completely continuous function. Okay, so we've got that. What else do I have to do? I think that's it for that section. So we've done Heavisides. So let's drop the hammer. Okay, so what am I talking about with this? Well, so the forcing functions that we've been dealing with are things that you can sort of imagine happening in physical, in the real world. So for example, I could take this thing and shake it up and down like this, and that's sort of a sinusoidal forcing function. You can see that there's something weird that goes on in the spring when I do that. I'm not being perfect. If I could have a machine do this, it would look a little bit more interesting. You might have some resonance set up. You could also imagine a forcing function that is linear, so I could pick this up like this, and as it goes up, and then I could stop it maybe. That would be or bring it back down and then stop. That would be an example of a Heaviside function times maybe a linear function. But this, so the hammer, the business with the hammer is that you can also demonstrate, let's see if I can get this on screen here. So I've got this, and I can take this hammer and just strike that. Ooh, that was interesting. And striking it imparts a force to this system over the course of a very small period of time. I mean, technically, it's not it's not a point in time, but it's a very small interval where the hammer impacts the bottom of this thing, and it's an elastic collision. You know this from your physics days, but you have this this energy that's imparted by the hammer into this spring mass system. And so this is, it's more of a physical thing than turning on the lights. I suppose you could imagine like a lightning strike in, a circuit gets hit by a lightning strike. That might be the electrical analog to that. I don't know that I can do this. But this strike, when I hit this, that is going to be modeled by a function that we're going to call the Dirac delta function. So this thing right here is the Dirac delta function. So it's this thing, the spring mass system might be at equilibrium right now, or close enough. And then I hit it with this. That's me hitting it with the Dirac delta function. Now the Dirac delta function is actually, I mean, it's not exactly going to be a single pulse like that. Like I said, it'll be in reality, you've got this force that is imparted over a very short period of time. But you can think of it like this. So I've got this, let's see if I can find a color that I can do. Here we go. So let's say that I want to impart a force at this point in time. so we're going to call that T equals A. Then right now, nothing is being imparted on the, no forces. And then all of a sudden, you have this shock. And that's a terrible, terrible rendition of the situation here. But you have this shock that is over the course of a very small period of time. In fact, that's terrible. I'm going to erase that and try again. So let's see, I go along, and then it goes up, and then it comes back down, because the hammer impacts the bottom of that spring, or that mass, and then it imparts all of the force, and the force is whatever area is in there. So the area is equal to the amount of force that's being imparted. Well, even this isn't a good model of exactly what's happening, because I don't know exactly. It's probably some sort of a bell curve. And so because we can't really say exactly how this is going to happen, what we're going to do is we're going to imagine taking this force, this amount of force that you're going to impart, and just put it into a single moment in time. And so the way that this is going to be drawn is something like this. This big spike that goes up to infinity, and then we continue on that. So you have to imagine that the area of this spike, this like thing there, that area is the amount of force that I'm hitting this with. So that amount of force is going to be the area of that thing. And this particular function is called the Dirac delta function. So delta looks like that. That's the Greek letter delta, lowercase delta. And the way that we're going to write this is t minus a. So that's the Dirac delta function at t minus a. And the area inside that. So you have to imagine that this thing is actually a very tall, skinny, it's got a little bit of area in there. It's just you can't see it because it's so skinny. But that area is whatever the force is. So you might have like this, A times that. So whatever number is in front of that, that's the amount of force that we're going to use. So here's a little tiny amount of force. And then I could go back and I could hit this with a lot of force. And it's a little bit more exciting, and then the mass there is probably going to fall off. But anyway, that's the idea behind the Dirac delta function, is that you have a single, this is a baseball. When you hit a baseball, that is essentially, it's an elastic collision that happens over the course of an incredibly small amount of time. So it's basically a Dirac delta function. Anything like this, lightning strikes, like I said. And by the way, those, what are they called? The electrical circuits that help you not blow your stuff. What is it?
GFCI.
Yeah, that's it. Thank you. Or whatever it is. Those are basically allow it to absorb those shocks. Very, and they have capacitors or whatever in there. But anyway, it smooths out the circuits, the circuit smoothers or whatever it is. Okay, so what is the? Turns out that the Laplace transform of the Dirac delta function, you've got it on your sheet there, so it's not very exciting, but this particular thing is just e to the negative s times a. That's it. That's all we need to know. So what's interesting about this to me is that when I impart a force to this thing, and I won't do it anymore because it's annoying to hear it go, squeak or whatever, but when I impart this force, what happens is that this mass begins moving, and it's as if the function, the solution to the, where this mass is, it's going along, minding its own business until I hit this, and then suddenly it's as if you have the Heaviside function times the sine curve, and it starts moving up and down. So this Dirac delta function allows you to model things like this, where you have an impulse or a shock. So I guess that half of you have this quiz, which is a little bit more complicated. Oh, there's the time. Oh, yeah, we got time. Let's do this, and then we'll talk homework preview. Although I kind of gave you a homework preview already. It's basically just doing Laplace transforms of the Heaviside function. There is homework for Wednesday that is Dirac delta function, if you get excited about this. Okay, so let's see if we can do this one now. And this one is actually going to be a little bit easier. I know it's surprising, but this one is easier than this one up here. So all the work that we did up here for this first order differential equation, this is actually a simpler solution. I know it looks more complicated with the pi and the 2 pi, but it is not. So let me just explain what that might model. That would model this. So I've got that. I guess I have to hit this 2 more times. So I've got this spring mass system. I start the stopwatch. After pi seconds, I hit this one way, and then after 2 pi seconds, I'm going to hit it the other way. So notice because of the minus, it's going the other direction. So it'd be something like this. I take the stopwatch. It's like, okay, pi, and then 2 pi. And I probably didn't do it quite the way it should have been, but that's the idea there, is that we're going to hit this thing twice, once one way, once the other direction. That's why the negative. All right, so let's see how this shakes out. Like I said, this is going to actually be easier than the first one. But let's go ahead and do this. Here we are. We have some volunteers. Travis knows how to do this y double prime, don't you? What's the Laplace transform of y double prime?
It is s squared Laplace of yt minus s y initial, which is 0, minus y prime of, y init.
Excellent. So minus 0, minus 0. Okay, 0s. I suppose I should put the s in there, right? All right, very good. Now we just need to do, this is just the same as up above, so I'll just write it as 4 Laplace of y. All right, now let's see if you can handle those Dirac delta functions. I thought you can. Megan, do you know what the Laplace transform of this first Dirac delta function is? Yeah, that's it. Huh? I mean, it's that simple. There's nothing weird going on. It's okay. Oh, reconnected. It's the YouTube connection for some reason. I don't know why, but our network here is not as robust as you would hope. I'm just kidding. I have no complaints about that. But I know that some of you have, especially when you're in your dorm room, and there's no, is that right? Dorm rooms basically are dead zones? Oh, really? I didn't know that. So they expect you to take your phone and plug it into the Ethernet? I've got this dongle I can put on my iPad. Okay, I'm just kidding. I always, I don't know, I have a strange sense of humor when it comes to things like that. Okay, go ahead, do it, and then we'll see how you did. I'm just going to do a little simplification, not much. All right. All right, you're probably already done. Let's just go ahead and take a look at this. It's going to be the Laplace transform of y, which is equal to e to the negative pi s over s squared plus 4 minus e to the negative 2 pi s over s squared plus 4. So there you go. All right, so who gets to tackle the first one? I know you all want to, but only Jackson gets chosen for this one. Do you know what the inverse Laplace transform of that first thing is? Or maybe you could get us started on this thing here.
Delta.
Oh, you mean this one?
Or, that. Okay.
Yeah, because this is, if you look at this over here, we're dealing with, it's not all by itself. The only time you have delta is if this is by itself. But once you have this along with something else, you're going to be using the heaviside function.
So it'll be heaviside,
I'm looking for myself here.
S minus 5.
T minus 5. Yeah, we're back in our own universe now.
And that's gonna be,
Yeah, let me pull this out. So you've gotten us started. So because this is your hesitation is helping me to let's just pull this over here and say what is the inverse Laplace transform of 1 over s squared plus 4? Because we're going to have to use it twice. So it's going to go there, and it's also going to go for this second one. So take a minute. And so now there's nothing weird going on. It's just 1 over s squared plus 4. See if you can figure out the inverse Laplace transform of that. And don't worry about shifting or anything. Just do that one. And I'll give you a moment, and I'll pick another volunteer. All right, hopefully you got something. You got it on your table. It's there. You can see it, can't you? But Darren, what is the inverse Laplace transform of 1 over s squared plus 4?
So, would it be 2 times sine of 2 times t minus pi? Oh, sorry, times t.
Yeah, so I like the 2, but I want to put it in the denominator.
Okay, yeah.
So yeah, the issue here is that when you look at the table, you're like, hey, wait a sec. What I really want is I want to see this. I want to have a 2 up here, not a 1. Well, if you put a 2 up there, you're going to have to balance that with a 2 somewhere. So it's going to go in the denominator. So that'll be there, and then we'll do the 1/2. And so it's 1/2 times sine of 2t. And now let's go ahead and do the shift. So let me get back to this maroon color here. And this is going to be times 1/2 sine of 2 times t minus pi. So yeah, you were right about the whole business about the pi, but I just wanted to do it in steps. Okay, so that's what I've highlighted in lime green is here. We still have yet to do this piece. Yeah, what do you think, Roston?
Could you just get rid of the minus 2 pi and the sine function just be 2t?
It would be.
Okay.
You're right. So Roston's showing off like the back of the book does with his trig identities. This is, in fact, so here, this is bonus. You don't have to do it this way. That this is, here, let me change colors just to, we'll do this. So this is sine of 2t minus 2 pi, and Roston recognized that, oh, wait a sec. No, it's okay. Yeah, so this is going to be sine of 2t. Yeah, this is correct. Because it's just, because the sine function has a period of 2 pi. So it's going to be the same if you move 2 pi. Okay, very good. But anyway, let's do the second one. Unnecessary, I mean, it's nice. And if you want to make it look like the back of the book, I guess you have to do it the Roston method. But let's go ahead and get this second one, and then we'll call it a day. So we have to subtract off this second one. Let's see if you can do it all. Clayton, can you do the whole thing, or do you want to do just a piece?
I'll try the whole thing. We have u of t minus 2 pi
Nice.
times the 1/2 sine of t times t minus 2 pi.
All right, very good. And you could use the Roston method there too to simplify that. The interesting thing about this one, I wish I had a rubber mallet, I'll just use my fist, is what's happening here is you hit this that way, and then you hit it again, and when you hit it the second time, it actually stops. At least according to that particular, if you graph that solution, it ends up being one cycle, and then it stops. So it's kind of funny the way that one works out. All right, so homework for Monday, though, is all just heavy side, but like I said, there's homework Wednesday. If you wanted to get ahead, it's all Dirac delta function. Also, you have a test Wednesday, and there is a practice test, I believe, online. We'll talk about that on Monday. So
on our
hopefully that
homework.
won't be too bad. Oh yeah, homework, you can make a stack somewhere. Maybe, you could be the first.
I did my homework from the day I was absent. on
Oh,
this as
nice,
well.
okay, hopefully I'll be able to see that, and if I don't, you can always let me know later.